what is a PFAS? Well, you probably read about it, but it's a per or polyfluoroalkyl substance. That's simply what it is. And there's, depending on the number of, or the source that you have, there's between 7,500 and 15,000 materials that would meet the definition of a PFAS. And it's a broad category of materials that they can be solids or liquids or gases. So AFFF foam is considered a PFAS. It's a per or polyfluoroalkyl substance. It contains materials called PFOS and PFOA. We'll talk about that in a moment. But they're considered PBTs. They're persistent, bioaccumulative, and toxic. If you look at any of the references to it, or checking with the EPA or other regulatory issues. It partitions to the groundwater, and as a result of that, their use is being phased out globally by the US EPA and other regulatory agencies. Halocarbon clean agents meet that definition of a per or polyfluoroalkyl substance, but unlike PFOS and PFOA, they're generally considered non-PBT. They're non-persistent, they don't necessarily bioaccumulate, and they're non-toxic. And so I don't work for 3M anymore, but I'm going to channel my inner 3M legal on this one. The last one there where it says non-toxic, because technically nothing really is non-toxic. Even water is toxic given enough of it. So the term that I would prefer that people use would be low in toxicity. But the other thing about this is that there's a lot of discussion about whether something is truly non-PBT or is a PBT. So there's a really kind of a mixture of those things, and we'll talk a little bit about that in a moment. But the one thing about here, and the reason for the title of the discussion, differentiating PFAS, is because if you read any of the articles that are out there, and I just cherry picked this one out of SFPE Weekly from a February article that they reprinted from Bloomberg Law. And the references in this article was all about PFAS. But what they were really talking about, they were talking about PFOS and PFOA in the use of foam. And so what happens here, and you'll see this in pretty much any article that's in any paper, any magazines. I just saw one that just came out that was just posted here by a blog that was talking about foam and materials that were considered PFOS and PFOA, but it was all referred to as PFAS. And that lumps them all together. And that's not necessarily the case that we should be doing that, because it confuses the issue. And I'll show you some reason for that technically here at this time. But what is a PFAS? The US EPA National PFAS Testing Strategy, identifying per and polyfluoroalkyl substances. Their definition is a structure that contains the unit RCF2CF, and you may have an R prime or an R double prime on that. Where that R, the R prime or R double prime, does not equal an H, and the carbon-carbon bond is saturated. In other words, it's completely filled with at least 3 fluorines on it. That's probably a very, very complicated description for people if you're not a chemical engineer or a chemist, and I am not. But that's the definition, and that typically would include most of the halocarbon agents, but not necessarily all of them. And in this case, FM200 and FE25 would not actually meet that definition. That's one of the definitions that's out there. The other one is the European Chemical Agency, or ECHA, in their February 2023 definition that came out in their proposed action. You'll see a per and polyfluoroalkyl substances are defined as any substance that contains at least one fully fluorinated methyl group or a methylene group carbon atom without any hydrogens, chlorines, bromines, or iodines attached to it. So and then it goes through a whole description of both. All that extra description really doesn't apply at all to the agents that are used, the halocarbon agents that are used in fire protection. So it's just the main description there, right up there, CF3X or XCF2X. So in this case, the HFCs, the FM200 and FE25 would indeed meet the definition of a PFAS in the European Chemicals Agency. So I wouldn't recommend anybody cherry picking a definition. If it's defined somewhere in the world as a PFAS, you'd consider it everywhere. So, like I said, the bottom line, EPA has not indicated any intent to restrict production of the use of FK5112 in the United States, even though FK5112 meets that definition, and the HFCs do not. But the ECA definition, all halocarbon clean agents meet the definition. But in the case of the proposed regulation that was proposed back in February, those materials are considered derogated. So the definition of derogation is to taking away or detraction from something as is in the force of law. In other words, a carve out in the regulations. And currently, the proposal is that all halocarbon clean agents are derogated from the proposed regulations. And that's not, and fire protection isn't the only one that's, fire protection clean agents aren't the only ones that are meeting with a derogation. The pharmaceutical industry is also having a number of their materials considered derogated out of that. ECA is reaching the restriction, they're dealing with the REACH restriction process at this point in time. They're going through that, and that's the European Chemical Agency. And the restriction process is a 3-phase process. They're currently in the second phase, which is it in itself has 2 phases to it, consultations and opinion development. And once they go through that whole process, there will be a decision and follow up on what that regulation is going to be in Europe. And from what I understand at this point in time, from the proposal, it would start in 2025, and for clean agents, there would be a 13.5-year process, or a 13.5-year time frame for to allow the industry to consider and possibly develop materials that would not necessarily meet the definition of PFAS and could replace the materials that are currently commercially available today. So that would take it out to, if my math is correct, about sometime in 2038. So they're assuming that somebody's going to come up with an alternative to the clean agents, FK5112 being the latest one that has been commercialized to any wide extent. There is another one that's used in a small handheld extinguisher, 2-bromo-333 trifluoropropene, but that's not really widely used like the HFCs in total flooding or FK5112 as well. So 2038, they're going to give us 13 odd years to find a replacement. They haven't found one in the last 2 decades. In my humble opinion, it's going to be pretty difficult to find something that's not a PFAS, number one, and then also something that's going to be as effective or more effective than what we have today. Right now, we're in that ECA committee's evaluation process, and by September, we'll have the committees will be adopting their opinions, and then committees will be sent to the European Commission, and whatever the European Commission will do at that point in time is anyone's guess. But there's going to be a lot of debate and discussions before it's final. So it's going to be a while. So, like I said, by September 25th of this year, they're taking submittals, and if your comments are without supporting evidence, it's unlikely it's going to have much of an impact. They are encouraging the industries to consolidate their submittals but there are others that can submit on their own. I believe FSSA is considering exactly how to do that at this point in time. So that's in the process right now. Like I said before, not all PFAS or polyfluoroalkyl substances are created equal. We talked about the PBT versus non-PBT. You can see the ones were persistent in the environment, either in the atmosphere, soil, and water. And that's kind of an important thing to talk about because most of what you're seeing in the news, in regulatory considerations, is talking about contamination in water and soil, but not in the atmosphere. So, and really, to be honest with you, there isn't a real definition that I have seen that would define exactly what persistent means. It's just, well, this material is there and it's not going away anytime soon. So that's considered persistent, but there's nothing technical that I've seen on that. And there's certainly, what would be the persistence in the atmosphere? Is it a couple of days, like you may have with a FK5112? Is a 30, 40 years, like some of the HFCs, or the longer lasting HFCs in the environment that may be out there hundreds of years, or the PFCs that are out there for 3,000 years? What's persistence? What's persistent? Is it something that's going to persistent and to stay there forever, or is it something that's going to break down eventually? And what's that level? So there's no real definition that's out there from an atmospheric standpoint. Similarly, how do you define bioaccumulative? There probably is more science to that. And toxic versus non-toxic. In my mind, for this industry, the measure for that would be what's in the standards right now and what's accepted by the US EPA and other regulatory agencies, where if it's acceptable for use in occupied spaces, that would be considered material that would be low in toxicity and available for use. So my guess at this point in time is, for the discussion of whether something is a PBT or non-PBT, it may be some mixture of both. And it certainly differentiates from what you see on the left-hand side of this slide, which is what you have in the C8 chemistry for AFFF foam. It'll be similar with the C6 precursors as well that are used in foam today. So PFOA and PFOS, they have a hydrophobic tail, fully fluorinated tail on that gives it the properties that allows it to float on fuel and snuff out the fire and seal the fuel from emitting the fumes to continue to burn. But then it also has the hydrophilic head to it that has an affinity for water. And as a result of that, it is designed to work in water. In fact, foam is, depending on the flavor that you're using, is between 94 and 99% water. And then the concentrate themselves even have a significant amount of water content to it. So it is definitely going to have an affinity for water. So, like I mentioned before, foam is mostly water, and so I have a comparison of a C6 fluoroketone or FK5112 and water, and I'm using those two for the reasons stated, that foam is mostly water, and any of the other clean agents, like I indicated before, if something applies to C6 ketone from a properties standpoint, chances are, because for the discussion of PFAS, it's going to apply to the lower boiling materials that are used as clean agents today, hail covering agents. So you see the properties there, the comparison with water and FK5112 as a boiling point, freezing point. But I'm going to point to you three of the properties: of the solubility, the vapor pressure, and the heat of vaporization. Now, the solubility of FK5112 into water is very, very low, approximately 1 ppm. That's about as much as you're going to get into water. And water into FK5112 in a laboratory scenario where you're actually trying to force it in there, the maximum that when I was in the laboratory at 3M, maximum we were able to get into FK5112 is 20 ppm of water maximum before it would phase split. So basically, the standards were NFPA 2001 and ISO 14520 have a maximum requirement of 0.001% by weight maximum for any of the clean agents, so that's about plus or minus either side of 10 ppm of water. So these materials do not have an affinity for water. They don't go into water, and they do not go into it, and they're not designed to work in water. The other properties that you have here is the vapor pressure and the heat of vaporization. Now, vapor pressure for FK5112 is very low compared to the other halocarbon agents, but it's compared with water, it's 12 times higher in vapor pressure than water. And you combine that with a heat of vaporization, or the amount of energy it takes for the material to become a gas, is 25 times less than water. So you combine those two properties. This material in a properly designed system, any of these clean agents, halocarbon clean agents, they will want to become a gas and very, very quickly, and then they would partition to the atmosphere. They do not partition to the water phase. They physically cannot partition to the water at all. In fact, with FK5112, in a laboratory testing, it was shown that it evaporates 50 times faster than water just sitting on a lab bench. This other comparison here shows the saturation curves in air of FK5112 in water. So you see that on the x-axis, you see the temperature, and on the y-axis, you'll see the volume percent in air and the vapor pressure in the atmospheres. And between the arrows there, you'll see the extinguishing or inerting concentration range for FK5112. We can do this for any of the other clean agents as well, but for FK5112, the range is between 4 and 10%. And at 20 degrees C, room temperature roughly, 68 degrees Fahrenheit, the differential between the maximum extinguishing or inerting concentration in air for FK5112 versus its saturation concentration in air is on the order of over 20%. You're going up to theoretical saturation in air of over 30% for FK5112. You would literally have to cryogenically force this material back by cooling it down in the room where it's discharged to get it to precipitate out in any meaningful way, and then to try to partition it to a groundwater or water phase. You'd have to take it down below 20 degrees centigrade, below 0 Fahrenheit, before you're going to meaningfully have this precipitate out. So that's that barrier right there is going to keep it from partitioning to water in the environment. It's going to be partitioning to the atmosphere. Number of ways of removing a material from the atmosphere, and a couple of them are oxidation, where you have reactivity with a OH radical, and it requires a very high reaction rate to produce a very short atmospheric lifetime. And one of the ways that you do that is get up into the mesosphere of the atmosphere in order to be able to do that. So you'd have to have a relatively low absorbance of UV light and a long atmospheric lifetime as a result. So it's not the way of removing FK5112 from the atmosphere. In terms of rainout, like we talked about here just a moment ago, the material does not have any affinity for water. It does not want to go into water or water in it. And so rainout And there's a number of references at the end of this presentation that would discuss that. It's not a mechanism for removal from the atmosphere. So the way it is, if these two are not the mechanism for removal, the way it is via UV absorbance and dissociation via photolysis. And that requires a strong absorbance in what is called a near UV light to produce a short lifetime. And near meaning near the ground level of the Earth. You look at here at absorbance to less than 200 nanometers, you're going to need to be in the atmosphere for hundreds of years in order to get to the mesosphere to be able to break down, as we showed there earlier. Less than 290 nanometers, be 1 to 3 years in the to get to the stratosphere. About 300 nanometers, your days to weeks to reach the tropopause and to break down. And then if you're over 300 nanometers, it's hours to reach the planetary boundary layer. So that's with the ketones, acetone, which is a very well-known material, the hydrocarbon acetone, that breaks down fairly quickly on the order of days in the atmosphere with a wavelength of just under 300 nanometers. For FK5112, you have absorbance of 305 nanometers of wavelength. So as a result of that, you're going to have an atmospheric lifetime. Depending on the study that was looked at, Gushin had 3 to 5 years, 3 to 5 days. Taniguchi had about the highest, about 1 to 2 weeks of atmospheric lifetime. A couple of 3M sponsored studies showed little less than a week of atmospheric lifetime. And so basically, if you look at this, the general consensus is this material will photolyze and lead to a lifetime of about a week. In fact, there was a study that was done after this presentation at the Halen Options Technical Working Conference that was done by a researcher in Spain by the name of Diana. And Diana used actual sunlight, not artificial sunlight like these studies did, used actual sunlight. And Diana came up with an atmospheric lifetime of 2 days. So about a week is a reasonable figure for that. So what's the atmospheric degradation mechanism? So it starts out with the molecule there, and you hit it with the 305 nanometers of wavelength, and it takes days to break down into a perfluoroalkyl or a perfluoroacyl radical. And once it gets to that point, it's going to readily react with oxygen to form another radical, continue on with the process. And then it reacts with the nitrous oxides to continue the breakdown in a matter of minutes once it's been split. It continues on then in a couple of ways. One goes to a CO2 and an ethyl radical, and that breaks down into that pathway into two molecules of CO2 and 5 molecules of HF. The other route that would go breaks down into a couple more radicals here. In one case, it goes to CO2 and 3 HF, 1 molecule of CO2 and 3 molecules of HF. And the other path, reacting with water, forms trifluoroacetic acid and 1 molecule of HF. So though that's the mechanism, you can probably find another mechanism for some of the other agents that are out there. I don't have those personally, but I'm sure the other ones do. But this is the balanced equation that you would have. The molecule results in four CO2s. One molecule of FK5112 would result in 4 molecules of CO2, 1 molecule of trifluoroacetic acid, and 9 molecules of HF. And you can see that on a percentage basis, with that breakdown, you look at about 24% of the product from that breakdown would be trifluoroacetic acid, a little over 38% HF and on a mass basis, and 37%. So when you get 316 grams per mole of ketone results in 114 grams per mole of trifluoroacetic acid, 20 grams per mole of HF, and 44 grams per mole of CO2. You multiply that by the number of molecules there, that gives you your mass. That's how that works. Just to wrap it up then, FK5112 evaporates 50 times faster in water. The other halocarbon agents will definitely do that as well, even more so. They'll have more propensity to evaporate and be partitioned to the atmosphere. None of the FK5112 and the other agents have little or no affinity to water. They will not partition as a result of the groundwater and end use. And they will partition to the atmosphere and be broken down via UV ray absorbance in about a week, FK5112. The other ones will have a different mechanism and will be longer. The bottom line, understand fire protection PFAS differences. That's the whole point of this discussion, is that PFOS and PFOA in foams, they partition to the water. We should also know that all clean agents, the inert gases and the halocarbon clean agents, they partition to the atmosphere. Also know the difference between PBT versus non-PBT. And then also inform your companies if you're a specifier or you have a customers, authorities having jurisdiction about that PFAS differences, because the industry, the media all conflate PFAS to make it all sound like it's all PFOS and PFOA, and that's not it. And lastly, stay calm.